Section 2.3.4, the energy of a continuous charge distribution. In the previous video, we discussed building charge by charge a discrete charge distribution and said that the minimum energy to do that was 1/2 times the sum of all of the charges times the potential at every point for those charges. Yeah, it tends to be the case that we want to extend this to continuous charge distributions. All right, that looks very similar, except we're going to swap out the sum with an integral. We're going to integrate over where the charges are, right? So that's a charge density. This is just specifically with respect to the volume charge density, but it could be a surface or a line charge density. The charge density times the potential times d tau. So we're integrating over space, all of the space that encloses those charges, or includes those charges. Okay, and we can evaluate that integral, but we're going to go ahead and manipulate this expression to get something else. Okay, so what I want to do now is rewrite this charge density using Gauss's law, remembering that Gauss's law in differential form gives us that the density over epsilon naught is equal to the divergence of our electric field. Okay, so I'm going to combine those two expressions, and I'm going to get that the energy is 1/2 epsilon naught del dot E times V integrated over d tau. Okay, now this looks kind of gross, except we can acknowledge the fact that this looks like a derivative, but there's a derivative of a function times another function inside of an integral, and that smells like integration by parts. So we're going to go ahead and do integration by parts here and get two integrals out. That's epsilon naught over 2 times minus E dot gradient of V d tau plus another integral. This is going to be a surface integral of V E dA. You might recognize one of these terms, this right here. The gradient of the potential is the negative of the electric field. So I get that 1 over epsilon 2, negative kill the negative. I'm left with this E squared d tau plus integral of V E dot dA. So I have a volume integral and a surface integral. All right, so the volume and the surfaces, the volume that you pick and the surface that you pick are not independent from each other. If I were to pick some volume of space that I wanted to integrate over, the surface is just the bounding surface. There are many surfaces that bound a volume, but there's definitely an easier version versus many hard versions. So the area that you choose must be related to the volume that you choose, and the volume that you choose is related in many ways to the volume of this initial expression. Now, if I have chosen a volume, as long as it includes all of my charges, it's an appropriate volume to choose. Okay, so I can pick any volume that I want. As long as it includes my charges, that's an appropriate thing to do. All right, and because I can pick any volume that I want, I can pick the volume of all space, all right, negative infinity to infinity. And when I do that, that means that I evaluate a surface that's infinitely far away. All right, and because that is infinitely far away, both of those are 0. right? And I can go ahead and rewrite this expression where that energy to create that distribution is just related to electric field integrated over the entire space. All right. If I choose some volume that's not, I can't make this, that's not the whole space, I can't make this next jump. But I can pick any volume I want, any surface that bounds that volume. And if I choose one creatively, I can pick one that's easy to do the integral of.